Hey there. This is a video tutorial going over how to access some climate data, specifically NASA climate data in Google Earth Engine. This walkthrough is going to cover how to access that data through the Python API for Earth Engine through this notebook that was put together in Colab. But you can also download this and use it, as a Jupyter notebook elsewhere. The intended audience here would be people, I think, that have a little bit of experience maybe with Earth Engine, but are looking to get more or interested in specifically these climate data sets that we're going to talk about, and maybe how to aggregate those to better suit their needs. So I think having a little bit of Earth Engine experience is probably ideal. If you're new to the Python API for Earth Engine, this might be a nice way to kind of ease into that. So you do need, in order to complete this, you will need an Earth Engine account, which is free. You just have to sign up, and it may take a day or two to get that activated, but you will need that. So like I mentioned, this is going to go over some climate data sets in Earth Engine, how to access them and how to use them. This tutorial was put together as part of a NASA workshop in 2022, focused on broadening the use of NASA data within the species distribution modeling community. But this walkthrough will be useful for anyone that's interested in using some climate data in Google Earth Engine, and these techniques could be applied to other data sets. I just happened to choose 2 NASA data sets to work with for the purpose of the workshop. So there are many data sets related to climate in Earth Engine. You can visit that link in this first chunk here and see all of the data sets that are tagged climate in the Earth Engine data catalog. Specifically, we'll be using the NLDAS-2 data, the North American Land Data Assimilation System data, and DAYMET, the Daily Surface Weather and Climatological Summaries data. Both are NASA data sets. Like I mentioned, this will go through using the Python API for Earth Engine, but if you're interested in completing these or looking at these in the code editor for Earth Engine, the JavaScript code editor, you can follow these links here and go to the code and basically complete this exercise there instead. It will be self-paced, so I'm not going to walk through that, but you can find the code there if that's your preferred platform. So in order to get started, we have to import the EE module, which comes already in Colab. You just have to import it into your notebook. And once you've done that, you need to run this authentication workflow. So if you run these 2 commands here, in the response, you'll get a link. You can follow that link and log into Earth Engine. Make sure to choose the account that you have access to Earth Engine with. Hit allow. You're basically saying, I'm giving Earth Engine permission to interact with this notebook, and then paste that security code or authorization token there, and it'll save it. So you get a message that says it was successfully saved once you're done, and now you're ready to use the EE module and access all of the Earth Engine data from the notebook. So like I mentioned, here are the 2 data sets that we're going to explore a little bit. And you can find more information about them through the Earth Engine catalog records for each one. So here's the record for the NLDAS, and here's the record for DAYMET. So feel free to check those out. And there's some information here about their spatial resolution and extents and things like that. The NLDAS data is hourly, and in some cases you may want to aggregate that to a different temporal frequency, so perhaps a daily frequency instead of hourly. So this will just walk through how to do that for one specific band within the data temperature. And so to start, you need to create a variable that points to the image collection on the Earth Engine server. So this first line is just establishing this variable NLDAS and pointing to where that is stored on the Earth Engine server. And anytime you want to access data in Earth Engine, you use this kind of syntax here. So ee.imageCollection is just saying, find this image collection, and then there's a string of characters for where that's stored to point to that specific image collection that you're interested in. If you go back up to these links here, when you're searching the data catalog for Earth Engine, you can find these specific character strings that you need to use to access the data or point to the data set. And this syntax is the same if you're accessing a different type of data. So if you're accessing a single image, it would be ee.image. If you're accessing like a feature collection or vector data, ee.feature collection, and then the character string of that specific object that you're looking for. The next line here just grabs the band names from the first image. So now that we have that variable, we're getting the first image with .first in the collection, and then .band names will get a list of the band names. And then finally, you can print those out using this line here, bn.getInfo. So in the code editor, you can just use the command print bn, and that would print the band names, or you could do the same typically in Python, but because we're interacting with the Earth Engine server, this .getInfo basically tells it to unpack that, bring it to the client side, and print it out for us. So it's just an extra step that you have to do when you're using the Python API for Earth Engine, but that's the way to get things printed to your actual notebook. So if we run this chunk, you'll see created a variable, and then we listed the bands here. So these are all the bands that are available in this NLDAS dataset. Okay, so now that we have our NLDAS data here, and we want to aggregate that up from hourly to daily, we need to first establish a time range within which we're going to aggregate the data. So in this case, we'll just use the month of May 2017 as our range. So you'll see in this chunk here, we're establishing two variables, a start and an end, and those are strings for the start and end date, so May 1st through May 31st of 2017. The next line here is getting the difference between our end date and our start date by day. And you can see these little wrappers that are around both end and start, the ee.date, that's just telling Earth Engine to interpret this string that we're giving it as a date. So sometimes you'll have to play around with using these different Earth Engine wrappers to make sure Earth Engine is interpreting the object that you're giving it correctly. These next two lines here are creating a function, which we'll use here in a second. But basically, this function is adding days to our start date. So for every day in the month, we want to get a new date that is the start date plus the number of days, which will make sense here in a second. So if we list, we're going to create this list of dates, but first we want just a sequence going from 0 to whatever the difference in our start and end dates is. So this goes from 0 to the difference between these two dates. And we're going to map that add day function over it. So in this case, in every number in this sequence, it's going to add that many days to our start date. So we'll get a list of dates corresponding to every date in May 2017. So if we run this and use getInfo to print out the list that we just created, you can see it doesn't make a lot of sense because Earth Engine is using Unix time or time since epoch to report these dates, which is fine. But if you are interested, you can try to reformat those just to print them out and make sure that you got the dates that you intended to. This is not necessary, but it's a nice way to just check that your function that you created and your list of dates is coming out correctly. So you can reformat the date here. We're just saying take all those dates and format them like this, like what our original string was. So 4-digit year, 2-digit month, and then day of the month, and create a new list. And then we can print it with get info. And so here you can see it worked as we wanted it to. We have all of the dates for every day in May 2017. So this next section is kind of the workhorse of the whole script and where the real computation takes place. And it's a little bit lengthy. I probably could have split this up into a couple of different lines, but I'll go through it as best I can. So we have that image collection, the NLDAS data. We're going to first say that we want to select the temperature band only. So now we just are using a single band from that image collection. And then we're going to filter by date. In this case, we're going to be mapping this over our list of dates. So for every day in this list of dates that we created, we're going to filter from that day to the next day, which is what this is saying. So the day in the list that it's currently mapping on, and then take that day and add 1 day, dot advance 1 day. So this filter, this date filter is inclusive at the start and exclusive at the end. So if you're mapping from May 1st to May 2nd, or filtering from May 1st to May 2nd, you're just going to be getting all of the hourly data from May 1st and not May 2nd. It's going to stop when it hits May 2nd. Then for that day, we'll get the average temperature, and then we'll set the time, this system time start parameter to the day. And that's just setting a metadata parameter in the data for us. Then we will create a new image collection by mapping that function, the mean daily function we just created, over our list of dates. And then we can look at the size here by printing it with .size, .getInfo. And like we expected, we have 31 images in that collection. So 1 image for each day representing the average temperature. Now we can visualize the data. So in this case, we're going to look at the average temperature for a single day, May 1st, 2017. The Folium library is a library that allows you to create dynamic maps in the Earth Engine API, and you can use the EE module to create static maps, but this tends to be a little bit more interesting when you create visualizations that are dynamic. I'm not going to go through all of the steps here, but anytime you want to use this, you can basically copy and paste this sort of framework and reuse it, just changing some things down below. So you'll just need to change your visualization parameters. So I've set this up since we're visualizing temperature, tell it the min and max, and then gave it a string, a list of strings for colors to use. You can, using this my map object, you're establishing your map, basically the location you want to start the map on and the zoom level that you want to start with. And then to the map, you can use .add EE layer to add whatever data you want, specifying in order here the image you want to add, the visualization parameters, which we created up here, and then a name for it. And so in this case, we're adding temperature, but we're using, because temperature is an image collection, we're using .first here to get the first image in that collection and just display that single image. We could use other operators here like mean or median and get, you know, a visualization of that data across the whole month. But in this case, we just want that first day in May. And then this line is just adding some controls to the map. And then the final one is telling Folium to display the map. So if we run this chunk, see down below, we'll get this nice dynamic map that you can move around and zoom. The layer controls are over here, and sometimes they get hidden by some other things, but you can see you can toggle this on and off. But basically this is the average temperature for May 1st, 2017 across the entire extent of the NLDAS-2 data. And this is the full extent of this data. Covers from covers Central North America, so a little bit up into Canada and a little bit into Mexico as well. Next, we're going to move into using DAYMET data, and DAYMET data is daily data. That can be, in this case, we're going to aggregate it to a monthly temporal resolution instead. Very similar to the previous example, we're going to establish a start and end date here. So we want all of the year 2017. So going from January 1st, 2017 to January 1st, 2018. Again, that end date in this case is exclusive. So the last day of data we're going to get is from December 31st, 2017. Here again, using that same syntax, we're going to point to the DAYMET collection in Earth Engine, and then we'll go ahead and filter by our dates. So this will filter out anything that's outside of our date range. Again, we can print the band names from the first image in the collection, but they'll be similar for all the images in the collection. So if we run this, we can see the bands here. So we have the daylight hours, precipitation, shortwave radiation, snow water equivalent, the daily max and daily min temperature, and then vapor pressure. And so in this example, we're aggregating daily to monthly. So for, again, we're going to use that same framework of mapping a function over a list of dates or a list of numbers. In this case, since we are trying to aggregate things to a monthly level, we just need a list of months. So there are 12 months in the year. We can just create this sequence from 1 to 12. And then that's the list we're going to map our function over. So here's where we create the function that's going to be doing all of the computation. The M here is month, so the number in that sequence that we just created, 1 through 12. And there are two variables that are being created inside of this function. The first is means and the other one is sum. So depending on what you're hoping to get out of the data here, you may want to think about summarizing things differently, but to me it makes sense, depending on the variable, we're gonna use temperature, two temperature variables, and precipitation. Depending on the variable, you may want to summarize things differently. So in this case, we're filtering by the month in question. So using this ee.filter.calendar range, filtering from M to M. So if this was the first month in the sequence, it would be from January to January, and telling it that this range is a month. So this is counterintuitive to what I said before about the ee.filter.date function, where the second parameter, the end date, is exclusive. Using this calendar range, it's actually inclusive. So if you if we were to change this and say we wanted to filter calendar range by month from month 1 to month 2, that's going to give us all of the data from January and February, which is why we filter it from January to January, So our start and end dates are the same month, but we're only getting data for 1 month, which is what we want. So just be aware that some of these date filters don't all function the same. And you can find out some information as if you hover over it, you can find out some information here, and you can see in this case that both the start and end are labeled as inclusive. But so once we filter by month, we're going to select the two bands that we're interested in. In this case, it's the minimum temperature and the maximum temperature. And then we're going to get the mean of that. So for every day in the month, what was the average high temperature and the average low temperature? The next line is where we're going to summarize precipitation. So using the same date filter, we're going to filter to whatever month we're mapping over in that list at the time. Select precipitation, and then in this case, we're going to use .sum to aggregate this. So we're going to get the total precipitation for that month. So take the precipitation from every day, add it up. And then we'll return these means, which we created, and add the sums band to it. And then use this .set to set our metadata so that we know which month is which. So we'll have a metadata parameter corresponding to the month. And now we can run that function or map that function. So we're creating this variable DAYMET month, telling Earth Engine it's going to be an image collection. And then within the parentheses here, taking that list of numbers 1 through 12 months and mapping this function up here by month that we just created. So now we'll get an image collection with those 3 bands, and there should be 12 images in this collection. So if we run this chunk, we can see we printed out the size of the collection. We have 12 images. So now we can again display these on a map, and we can display all 3 bands. We'll just display it for a single month, May 2017. Just like before, we're going to use some visualization parameters to tell Folium how to display our map or our layers in our map. And in this case, since we have 2 different variables, I set up 2 different visualization parameters. So we have the precipitation visualization and then the temperature visualization. Here again, we create a map object, and then we're going to create 3 different images to display. In this case, we're using the ee.filter.equals to filter by metadata. So we can say, because we set that metadata parameter month to equal whatever month, the number of the month that we had aggregated the data to, we can use this to filter out the data that way. So we're saying, give me the data, the images corresponding to month 5, or the image corresponding to month 5, select the precipitation band, and then this .first is necessary because even though this filter is going to return just a single image, Earth Engine still interprets it as an image collection, but an image collection with only 1 image in it. So using .first, that then tells Earth Engine to select the first image in that collection, which there's only 1. So you'll get the only image there. You could probably use like a ee.image wrapper to accomplish this, but this is the way I tend to do it because it's quick. So that's why you see this .first at the end, even though there's only 1 image in the collection. So the same thing here for the minimum and maximum temperature variables. Select those and use .first. And then we add all 3 of those layers to the map, add the layer controls again, and display. And if we scroll down, you can see all of those layers have been added to the map. Again, you can pan around, zoom, and these are, DAYMET has a larger spatial extent, so it covers all of North America. So if we zoom out, you can see the full extent. And then over here, you have the layer control, so you can turn things on and off. So if we turn off, that was maximum temperature for the month of May. This is minimum temperature for the month of May 2017. and then there's total precipitation there. In all of these cases, at least with temperature, it's, you know, obviously ranging from red to blue, is hot to cold, as you would expect to see on that map. Minimum, same, and then it's reversed for temperature, so or for precipitation, excuse me, so less precipitation in red and more precipitation, kind of ranging up from yellow to green to blue. This next section is covering something that most people in the, or a lot of people in the workshop mentioned being important, was detecting extreme weather events. And this is just kind of a first sort of look at how you might start to get at this using DAYMET data. I am not a climate scientist, so this is my kind of interpretation about how you might detect some extreme events given the data in DAYMET. This is certainly not, you know, the only way to do it or the best way to do it. This is just kind of some ideas for how to get started and what you can accomplish with the data in Earth Engine. So again, we have this function that we created above. We're just going to continue to add some variables to it that might shed some more light on when abnormal or extreme weather might be taking place. These first two lines are the same, with the exception that I've renamed the bands here. So since we're going to be adding more bands that deal with temperature and precipitation and would just be named something nondescript automatically by Earth Engine, I just wanted to explicitly rename things so that we can keep track. So you can see the dot rename, and then this is going to be, you know, the average low temperature from the day for every day, or the average max temperature from the day. So kind of the average high and low temperature for each month. I renamed the precipitation total. And then this last line is new, but it's basically using a different operator here to summarize the data. So get the high temperature from every day and the precipitation from every day, and then report the max for that month. So what was the highest daily temperature and the highest daily precipitation amount? And so that's what we've renamed here, the Tmax, max, and precipitation max. And we add all those bands together that we've created, and again, set the month, map it over our list of months again, so 1 through 12. And then in this case, we're going to print the size again, should be 12. And we can print the band names just to confirm that those new bands are in there. And you can see that they are, and things have been renamed correctly how we wanted them to. So a maximum, you know, what was the highest temperature for the month and what was the highest daily precipitation amount for the month might start to give you some information about extreme events. Another idea is to use some of these created variables to make some more computations. And again, these are not, you know, potentially the best way to do it. These are just ideas that I had about how you could start to go about this with the data. So the first three lines are exactly the same as above, but we're adding these two new variables here, extreme temp and extreme precipitation. So for extreme temp, since we created a maximum temperature, so we know whatever the highest temperature, the highest daily temperature was for the whole month, it might make sense to look at how that compares to the mean to get a better idea about the distribution of temperature across the whole month. So if you think about a nice tight distribution where the temperatures were pretty, you know, closely surrounding the mean, where you didn't have a lot of variation in temperature, you could see that the mean and the max would be relatively close together. But if there was a single day where there was a massive heat wave or something like that, or a few days where there was a massive heat wave that are way above the mean, then that distance is going to be larger. So you could use this. That's what this extreme temp variable is get the max temperature for the month and then subtract the mean from it. And we're renaming that temp D mean, so difference between mean and max temperature. And then for precipitation, because our precipitation is reported daily, and then we also created a variable for the total precipitation for the month, it might be interesting to see whatever the maximum daily precipitation, so there was whatever day had the most precipitation for the month, what percent of the total precipitation is that? So if that percent turns out to be 100 or 1, then you would know that that particular pixel got all of its rain on one day for the whole month. So if there was a long stretch or a couple days stretch of a lot of rain, then you might find that the percent of precipitation for a day out of the total could be very high, which could indicate that maybe this was an abnormal rain event or out of season precipitation event or something like that. So we create these two new variables, add all of them together, and then create our image collection again by, and when I say add, I just mean combining the bands, so basically stacking these layers that we've created. And then we map that function over our list of months again, and we'll again just print to show that our image collection has the correct number of images, and then we have the bands that we intended. And finally, I'll talk about exporting data. So, currently we're just using data on the Earth Engine server. We can run computations and visualize things, but if you want to actually get data out of Earth Engine, there are a number of ways you can do it. If you're just interested in the values for certain locations, you can extract those and export them as a CSV. This example is going to talk about actually getting the image collection or the images that we've created out of Earth Engine. So we can use them in a local environment and run our own analysis somewhere else. So we'll use the Earth Engine also has a lot of vector data sets available. And in this case, we're going to use the Tiger data set that the Census Bureau creates for state boundaries. And so we'll export the DAYMET monthly data for the Western US using that Tiger data set as our boundaries. And so feature collections in Earth Engine are made up of the shape boundaries, but also a bunch of attributes. In order to export, we just care about the boundary, the geometry, the outline of it. So we'll just extract that outline. So like we did before with the image collection, now we're referencing an EE.feature collection, and we're going to get the state boundaries. We create this list of state names for the states that we're interested in for exporting our DAYMET data. I just listed states in the Western US. You can adapt this list however you want, and it'll export for other states. And then this last line is creating a region of interest variable, ROI. It's filtering the Tiger data, so all of the state data by our list that we've created here. And so in the metadata for the Tiger data, the state data, there's a property called name. And then we're saying if any of these states in our state names list here is matches a name, we want that state. And the last part here is turning those features into just geometry objects, so just the outlines. And then this dot bounds is not necessary, but I think it makes for a little neater export. It just gives you the maximum bounding geometry of all of those states. So you're going to get some portions of other states surrounding it, but you're not going to get the jagged outlines of the state. But if you're interested in specifically just the state data, you can eliminate that dot bounds command right there. And this is just a reminder. I know we've done this quite a few times, but we can print out some information about the image collection, the size, the bands in the image, and then I've added another line here to print out the month IDs. So you know, they should be 1 through 12. You can use this aggregate array command to aggregate any metadata property in your data. So we have that property month. We want to get the array, like see the full list of months in our image collection. We can use aggregate array. And there you see we have 12 images. There are the bands. And then we have the month IDs here. So Earth Engine's set up to efficiently at least export images rather than full collections of images, so individual images. There are ways to export entire image collections using, you know, you can use a for loop. There are some batch tools like this one that's referenced here that you can check out on GitHub from Rodrigo Principe. And they work well. The for loop especially is better if you're running that on smaller collections. I guess in general, any loop in Earth Engine is better if you're using it on smaller collections, just because you're kind of mixing client side and server side objects, and they generally advise against it, but it can be done. But this example is just going to walk you through how to select an image, a single image from the collection we just created, and export that. There's two things to note here, and I've touched on the first one already, but using this .first command. So again, even though we're filtering our image collection down to just one image, we still have to use .first to tell Earth Engine that we want the first image, the only image from that collection. And then the second thing is this .toFloat here is just making sure all of the bands are the same data type. You'll run into errors if you try to export multi-band data where the data is of different types. So if you have some integers and some floats, it's not going to allow you to export that. So you just have to decide on a data type and convert everything to that. So there's the last chunk here is where we'll actually export the image, and you can find out a lot more information about exporting on Earth Engine's developer guide with that link there. But basically, you have to create a task object or a task variable, and it's a little different if you're using the code editor, but in the API here, you have to create a task object with certain things, certain parameters identified. So the first is the image, which is what we just created above, this image to download, and I actually need to run this here. I need to run this here as well. I'm just realizing I forgot to run those. So now we have our image is our image to download, which we just created above. The description, this is what will appear in the code editor or the task manager, which I'll show you in a second. A scale, which can automatically defaults to meters. So 1,000 meters is the native scale of DAYMET. We're going to keep it at that, but you can change that. The region, so the ROI is the variable we created above to represent Western states. And then you can give it a name. This is what's going to appear in Google Drive. Your coordinate reference system, in this case, we're just using WGS84, and then a file format, which it defaults to GeoTIFF, but I just put this in here so that you know you can explicitly state the file format. And then you just have to run task.start to get this going. I'm not going to run it because I actually have already done this, but I'll show you once you would run it. If you went to your Earth Engine account and went over here to tasks, you can see your task is going to appear here. And you could go to the task manager too to get more info about it, but this task ran in 5 minutes. And then if I go to Google Drive here, I can show you that here it is in my Google Drive ready for me to download. So that's how you get data out of Earth Engine, and how you use some of the NASA climate data that is in Earth Engine from the Python API. So hopefully this was helpful. I would appreciate if anyone does find this useful, sending me an email or getting in touch and letting me know. If anyone runs through this and finds issues, I would love to hear about that too. So I welcome any and all feedback. Hopefully this was helpful for workshop participants especially, but also for anyone else that might have come across this. And you can find these on our GitHub page as well, which I'll try to add a link to future versions of this notebook. But thanks, and look forward to hearing any feedback anyone might have.